So, yeah, so today I'm gonna talk about inflation. I'm gonna talk about perturbations during inflation, and then let's see how far we can go. Um, yesterday we talked about how inflation solves the horizon problem. We talked about how long inflation needs to last to solve those problems, and so on. We mentioned the fact that I forgot to draw ourselves. So we, I mentioned the fact that we want inflation to be long enough so that the co-moving distance associated to observable universe becomes small enough that it is a short physical distance, smaller than the Hubble expansion rate at that early time. Maybe even smaller than any other important relevant physical scale in the problem, so that we cannot have perturbations at those scales. It's just energetically impossible to have fluctuations there. And once we achieve that, then these 2 points will be approximately homogeneous. Now, as we go forward in time in this picture, at some point this distance becomes a border of the horizon size. And at that point, then it is, one cannot argue that there will not be fluctuations. In fact, as I mentioned before, this is an accelerated expansion universe, an inflating universe, and there we have a horizon and we have fluctuations, thermal fluctuations, with a temperature that is determined by the curvature scale of the background, which is the Hubble expansion rate. So once this distance becomes a border of the, so remember that as we go forward in time, then the physical size of this co-moving distance becomes bigger and bigger compared to the Hubble, because we are in a cosmology where d by dt of h times delta x, where delta x is a constant, d by dt of h is larger than 0, which means that this as we go forward in time, this becomes a bigger and bigger physical distance. Eventually, this physical distance becomes the order of the Hubble, and then we have fluctuations, these thermal fluctuations that we are going to study in more quantitatively later, or today. But I just want to give you the physical intuition that what happens. So once we get to that scale, then there will be some fluctuation. Oh no, maybe I use a different color now. What's a good color? Green. What? Oh, okay. Oh, let's use pink. So there will be a fluctuation at this scale. Now let's consider another co-moving distance. So this corresponds to the co-moving distance of order of the horizon size. So now let's consider a smaller co-moving distance, say half of the size of the horizon size. So here. Now what happens to that? So let's consider the past light cone of that. So now this corresponds to half of that wavelength, or half of that distance. So it means that we have to wait longer until that distance, that shorter distance, becomes a border of the horizon size. How much longer? Remember that we are in a situation, in a geometry, when W is close to -1. When W is close to -1, the Hubble expansion rate is approximately constant, which means that the scale factor is approximately growing exponentially. So it's going as e to the ht approximately. So therefore, if I want to, I should also remind you that this combination, but this is useless, right? So this combination H delta x, we want to see what is the point when this becomes of order 1. This is equal to so the comoving Hubble parameter is a dot, so this is a dot delta x, which is h. Remember, this h is h during inflation times delta x times the scale factor. So we want to see when this is becoming of order 1. So if I consider this, and then now we are saying that approximately we have this equal to h delta x times the scale factor goes as e to the ht. So if I consider if delta x goes to delta x over 2, then the time that I need to wait for this shorter distance to cross the horizon for this combination to become of order 1 for that shorter distance corresponds to t going to t plus log of 2 divided by Hubble. So it will be just a shift in time. So therefore, what happens is that for that shorter distance, after some time shift, there will be that shorter distance will be of order of the Hubble, and then there we have another fluctuations of order de Sitter fluctuation, thermal fluctuation that can generate difference between the two patches. And then we can continue this. So consider now a distance that is half of the previous one. And this means that now I should wait for another time interval, which is, again, a similar time interval. And after that, there will be a horizon size fluctuation. So this interval between these are approximately the same. So this is this delta t is over the log 2 divided by h. Oh, by the way, this is a plot of conformal time. So while it's important that I'm talking about the physical time. So let me say here, delta t 1, 2, and then here we have delta t 4, 2, no, delta t 2, 1, delta t 4, 2, and so on. So these are time intervals that are the same and corresponds to the scales that are exponentially becoming smaller and smaller. We also saw that during inflation, we have this slow roll solution. What was the implication of having a slow roll solution? It was that things are not changing very fast. So the expansion rate, for instance, is changing very slowly. Hubble parameter is approximately the same. Properties of this background geometry is approximately the same as time passes. So there is an approximate time translation symmetry in this inflationary solution. That approximate time translation symmetry, as you can see from the simple examples, translates into an approximate scale invariant. So that's why inflation creates an approximately scale invariant spectrum. There is some deviation from this scale invariance because the inflationary potential is not exactly flat. So with time, we are slowly rolling down. Therefore, the expansion rate is slowly changes. W is a bit different from -1. This small deviation corresponds to these deviations that we get lead to deviations that we get from a scale invariance. And those are the tilts that we compute, tilt of the scalar and tensor power spectra. Those tilts will be related to the slow roll parameters. Okay, so now we want to do this a bit more quantitatively. So I take just the scalar field, the inflaton field, which is in general a function of time and x. Before we just took it to be homogeneous to get FRW solution, but of course our universe is not perfectly homogeneous, so we take phi to be a function of t and x and divide it into a background and perturbation. So there is a background that gives us the background, the slow roll solution. Let's call it phi naught of t, plus fluctuations that I showed with the curly phi. And we want to find the linearize in this perturbation and find the equations of evolution of this linearized perturbation. So the equation of motion for the scalar field, I wrote it the previous time. I just write the answer when you perturb it to the first order. So I get phi double dot of, oh, and I'm also going to the momentum space. I think by now you have seen this very many times, so I shouldn't need to repeat these steps. That's how I'm going to the Fourier space. So in Fourier space, the equation of motion for this phi would be k squared over a squared phi of k. And then there will be a contribution from the potential, phi double prime evaluated on the background times phi k. This is equal to 0. So this is the linearized, the equation for the linear perturbations. Now we can also remember that we introduced this eta parameter that is supposed to be much less than 1. Now the smallness of eta parameter translates into the statement that it's a different color. No, green. So the fact that eta is much less than 1, it translates into saying that this v double prime is much smaller than h squared. Which implies that in this equation, I can neglect this term compared to the other ones, at least for this first treatment. Then later I'll come back to the importance of this term. But for a first treatment, we can basically ignore this and treat these fluctuations as a massless term. Why? Because either we are in a regime when k squared over a squared is much bigger than h, then obviously this term is smaller. Or k squared over a squared is much less than h, then this term is the dominant one. But still, this one is the small perturbation. Okay, so for now I neglect that. And another thing that I'm gonna do is to rewrite this equation very quickly in terms of the conformal time. So now prime means the conformal time. This prime is different from that prime. This prime is with derivative with respect to phi. This is derivative with respect to the conformal time, which is this. And in terms of that, what we are gonna get is this equation. So phi k double prime plus 2h phi k prime plus k squared phi k equals 0. Of course, this is not an approximation. Now, in this equation, we identify two two extreme regimes which are very important. Of course, these two extreme regimes is something that you have seen it before. For instance, in the CMB lectures, there are the superhorizon and subhorizon regimes. So, superhorizon regime corresponds to K. Superhorizon, no, subhorizon. Let's do first subhorizon. So subhorizon corresponds to subhorizon corresponds to K larger than H, much larger than H. In this limit, the solutions to this equation, in that limit, this term will be a perturbations and the solutions are oscillatory. And then this term will gives a modulation of the amplitude of oscillations. So in that regime, the solution will look like, and this analysis that I'm doing now is general. It doesn't really depend on the fact that we are in an inflationary background. This distinction between superhorizon and subhorizon regime. So there are two solutions which are oscillatory. C plus over the scale factor e to the minus ik tau plus C minus over A e to the plus ik tau. And then the other regime is, the other extreme is superhorizon. K less than the comoving Hubble. And in this case, solutions are usually algebraic power law in terms of the powers of the scale factor or the conformal time. So here we get phi k of tau equals a constant. So constant is obviously a solution because when I can neglect this term, then a constant would go through, and then there will be another solution which will be a decaying solution. And it's given by integral of d tau over a squared. Now, if we are in an inflationary background, then we can do this in a given a of tau. This integral can be done. For instance, if we approximate our background expansion by the theta, then this solution goes as 1 over a cube. But as you see, this is something that is decaying, so with time it becomes negligible. So in the superhorizon regime, one be dominated by the constant. Okay, so now it is useful to go back to this plot that we have for the time evolution of the comoving Hubble parameter as in different cosmologies or different eras. No. So do this. Okay, so now let's plot this diagram. So remember here we had log of 1 over co-moving Haber in terms of log of A as a proxy for time. And then there were various eras. So there is radiation, there is matter, and there is lambda, and then we have inflation. And now we want to consider particular momentum. Remember that this momentum is the momentum that we talked about here is the conjugate momentum to the co-moving distance, right? So we are talking about co-moving distances, not physical distances. So therefore, that momentum corresponds to a length scale here. 1 over that k corresponds to a fixed co-moving momentum in this diagram. So here I should just consider a fixed line which is log of 1 over k, a constant co-moving distance. And let us for now focus on this. So let's for a moment forget about having inflation and focus on this part of the diagram. So on the radiation dominant, on the lambda CDM part of the diagram. So now what we see is that in this phase, except for the last part, which corresponds to the lambda dominance, except for that last part, what happens is that given co-moving wavelengths or given modes start their life in the superhorizon regime, and then as time passes, they enter the horizon and become subhorizon. So they start by being in a superposition of the constant and decay mode, which very soon becomes dominated by the constant mode, and then after some time they enter the horizon and then become oscillator. So here we have oscillations. Here we have the solution, which is a superposition of a constant and a decay. On the other hand, if we now consider the full picture, including inflation, then those modes actually start their life in the oscillatory phase. And in fact, as we go further back in time, they will be oscillating faster and faster. This is equivalent to the statement I was making before. This co-moving distances correspond to physical distances much shorter than the horizon size. Okay, so now this is the very important feature of inflation, which is that if we didn't have inflation, we know from observations that we have cosmological perturbations that they start their life in the superhorizon regime. How do we know that? This is what Julian explained. We know this because we see the acoustic peaks in the CMB. So we know that if we consider modes which are a random superposition or fluctuations which are a random superposition of the two modes, the two oscillating modes, then every one of them would have a different phase. And therefore, when we look at the CMB CLs, those phases would cancel and we would just get a broadband. While because or assuming that the modes start their life in the superhorizon regime, then the decay mode becomes negligible, and we start with only one mode, and that becomes a particular superposition of the two oscillating modes. So every fluctuation that we have has the same superposition of the two modes. Therefore, they are all in phase, and therefore, when we look at the CS, they all oscillate in the same fashion. So we have very good evidence that the modes start their life in the superhorizon regime when we are in the late phase of the cosmology. Now, in this lambda CD, or in the Big Bang, hot Big Bang cosmology, that would be, if we wanted to explain this, that had to be put in as some initial condition that we don't know, we cannot explain any reason for it. It would be just some input in order to explain the data. In the inflationary scenario, on the other hand, these modes start their life in the subhorizon regime, and here there is a very good argument to determine the state of this fluctuation. So in particular, the state of these fluctuations is determined by saying that once we go in this subhorizon regime, it's basically a common sense argument. We don't have, when it becomes very high energy, then we don't have enough energy budget to excite them. So if they are extremely high frequency, they should be in vacuum. Starting from that, then these fluctuations, as we will see, will turn into superhorizon fluctuations, which are, okay, they are a combination of the growing and decay, or constant and decay mode, but the decay mode becomes irrelevant, so the constant mode survives, and then the rest of the story follows. So essentially, these vacuum fluctuations here, which then will be promoted into the constant fluctuations as superhorizon modes, what we can also think about them as the thermal de Sitter perturbations that are being stretched to superhorizon distances, they would be the origin of what we observe. Okay, so how does it work? So this is the part in which, so far, the whole analysis was classical. I just was talking about different modes, different solution of this ODE that I find for any K mode. Now to talk about the state of these perturbations, now I have to go to the quantum theory, and this is the point when now I should quantize the field, and this argument, after I quantize it, then this argument based on Heisenberg uncertainty principle can be quantified, right? So here I'm saying that short distance corresponds to high energy. Of course, these are things that is based on the quantum mechanical intuition. So now I'm gonna switch to quantum field theory. So far it was classical. By the way, if there is question, please ask. Quantize 5. So first I write an action for this linear perturbation. So a quadratic action from which the equation for these perturbations will follow. Oh, okay. Why do I write the action? Because I want to determine, evaluate, find the conjugate momentum to the field phi, and then impose the canonical commutation relation. So that's how we quantize this. And of course, it's a free theory, so we can go to the Fourier basis, and in the Fourier basis, it becomes a sum of a set of harmonic oscillators. So we quantize them like harmonic oscillators. Yes? Oh, yeah, so remember that I ignored the, where is this? Remember that there was a mass term here, but I argued that this mass term is negligible. So for now, yes, we consider mass. Increases the size. You mean the amplitude of these perturbations? I'm gonna write the solution for you in a bit. Well, I guess it depends a little bit on. No, in fact, no, the size is decreasing. The sizes of perturbations decreasing as they expand. It's an easy way to see it. You have a massless field, right? Field in 4 dimensions has dimensional energy. So vacuum fluctuations of modes with a particular momentum can only depend on the momentum itself. It's a massless field. There is no other scale in the problem. So quantum fluctuations at a given scale of a field, a scalar field in 4 dimensions, are of order of the associated momentum, so 1 over that distance. As your distance expands, that decays. However, if you are in the theta, if you were in some other decelerating FRW, then those would keep going down. In the theta, what happens is that as they expand, once they arrive to the horizon size, then they become frozen. Other questions? You have. Okay. So yes, I'm writing the action because I want to find the conjugate momentum. Okay, now I'm switching to momentum basis. I mean Fourier basis. So we vary the action with respect to phi prime k. Well, actually, let me not do that. I leave it as an exercise. So here we find a squared, what? We find a squared phi prime. But now I switch to the momentum basis. So in the momentum basis, the field becomes various Fourier components become like harmonic oscillator. Not exactly because you copy phi k to phi minus k, but you can choose a basis, a different basis that is diagonal. Or if you work with phi k, then if you want to quantize it, like a bunch of harmonic oscillators, then the creation and annihilation operators appear in this funny way. When you have FAK, they create the annihilation operator for mode k times some mode function f of fk of tau that I'm gonna write it explicitly in a second, plus a dagger of minus k. And if the star of k, f doesn't depend on the sign of k. F only depends on the amplitude of the momentum. While here, these are actually all vector. Okay, so the fact that for f, I don't write f of minus k here is just because this k is the amplitude of this momentum vector. So it doesn't care about whether this momentum vector pointing this way or the opposite way. What is this f? F's are the solutions of that equation that we had before. So F's are essentially solutions to this, which have this asymptotic behavior. But we can find the explicit answer in the limit that we can approximate the background cosmology with the theta. So if we can think about this as approximately the theta, then Fk of tau is gonna be a constant that would depend on k, the amplitude, the magnitude of vector k, plus I k tau times e to the minus I k tau. This amplitude, this constant that appears here, will be fixed by requiring that the canonical commutation relation holds. So canonical commutation relations in real space is that coordinate momentum can commute to I. If it is, we are talking about fields, it means that field and the conjugate momentum to the field commute to the delta function of the x minus y, where field is at x and momentum is at y. Then we can translate that to the Fourier basis, and in the Fourier basis, it will be Fk of tau pi k prime of tau equals I times 2 pi cube delta 3. So a momentum conserving delta function, delta 3 of k minus k prime. And this requirement fixes that unknown a of k to be h divided by the square root of 2 k cube. Okay, so far I quantized it. I haven't said what is the state of the system. The state of the system is now determined based on this physical argument that we want these modes to be in vacuum when they are deep inside the horizon. They want them to be unexcited. And that means that the operator that multiplies the positive frequency mode function have to annihilate this state, like harmonic oscillator. When A acting on this state annihilates it, we are in the vacuum. So and this state has a name. It's called Bunch-Davis vacuum. Bunch-Davis. I think it's called. Sometimes it's called adiabatic vacuum. They say the idea is that you adiabatic. If you are in vacuum but you have a very high frequency modes, then as you stretch the background so that the frequency changes, if it is changing very slowly, then it is an adiabatic perturbation, and you will stay in the vacuum. Like this change will not have enough energy to excite. So it has various names: Bunch-Davis, adiabatic, Arthur-Hawking. So this is the state that we choose, and and of course it's important the way I define A. A is the one that multiplies the mode function that oscillates as e to the minus I k times tau. So this is the choice of the state, and then we can compute what is the variance of the perturbations of this field in this region, or at any point, but in particular we are interested in the variance of these perturbations in the superhorizon region. You'll see why, or you already know why probably. So if I ask what is phi k of tau, just the 2-point function, phi k prime of tau in this Bunch-Davis state. This is equal to h squared divided by 2k cubed, 1 plus k squared tau squared, times the momentum conserving delta function. So 2 pi cubed delta 3 of k plus k prime, which in the limit of, in the super horizon limit, when k is much less than curly h, in this case it means that k times tau absolute value is much less than 1, it becomes, it goes to something simpler. Basically, this extra term here becomes negligible, because as we go towards late time, tau actually decreases. Oh, I should have maybe said this. So this tau variable, the conformal time, of course, the origin of it is arbitrary, but for inflation, it is very natural to choose the maximum value of tau to be 0. Also, that's what I have done in this plot. So during the inflationary phase, tau is going towards 0. Tau is negative and is moving towards 0. So late time means small absolute value of tau. So late time here means that this k squared times tau squared term goes to 0. Okay, so now in this limit, this becomes simpler. Becomes just h squared divided by 2k cubed times the same momentum conserving delta function. Okay, so now I want to do a comparison. So let us look at the ratio, or maybe it's a good time to, let's go to a new page. So what do we do? So of course we see in our universe, in the late cosmology, we never talk about quantum perturbations. Everything that we discuss, like in CMB or what Marco discusses, they are all classical fluctuations in density or temperature and so on. While here I talked about quantum fluctuations of this. So it's often a question of how do we make this transition between a discussion that was quantum into a discussion that is classical. So maybe it's useful to make this little computation here. So let us again go back to this commutation relation. But now I want to compute, look at phi k, the commutator of phi k and phi k prime dot. Remember before it was prime, now I write it dot. Just because dot will correspond to taking derivative with respect to the physical time. although it doesn't really matter for this comparison. So I want to compare this, the commutation between phi and phi dot. So before we looked at the commutation between phi and the conjugate momentum, right? Now I want to look at phi and phi dot for a reason that becomes clear soon. So let us look at the commutation ratio of the commutator of phi and phi dot and the expectation value for this same, for the phi k. So I'm talking about phi and phi dot. So just to make the whole thing dimensionless, I divide it by the variance, h times the variance of the same quantity. Right, so now I'm talking about the dimensionless quantity, right? Phi dot is 1 over time times phi. There is h in the denominator, so it makes the whole thing dimensionless. So this ratio we can compute. Of course, both of them contain a delta function. So really, I care about the amplitudes of that delta function. They cancel. The delta functions are the same. What you will get is 2k cubed divided by a cube h cubed, or k cubed divided by the Kerlish comoving Hubble cube. Now remember that in the superhorizon regime, this ratio is small. And in fact, since k is constant, h is approximately constant, but a is approximately exponentially increasing. This whole ratio is exponentially decaying in time. So this is extremely small. This is exponentially small. It goes to 0 in the superhorizon regime. Now, what is the relevance of this? When this is extremely small, then it means that to a very good accuracy, you can treat this phi field as a classical field. So if you have a finite resolution for measuring phi, then when the commutator is much smaller than the typical value of fluctuations, it is legitimate to talk about the field as a classical variable. What is the difference between a classical field and quantum field? A classical field is something that you determine its initial condition and initial velocity, right? Say for a particle, you can specify initial x and initial x dot and have a history, a classical trajectory for its motion. Similarly, for a classical field, you can specify initial value and initial time derivative, and then talk about the history, a classical history. Maybe to give a very simple example, more explicit, let's actually talk about this particle. So, analogy. Heavy particle. So now I have only one quantum mechanical degree of freedom. X and P always commute to I. But now if I ask about X and X dot, this is I over M, the mass of this particle. Now imagine that I have a resolution. My measuring device has a resolution that is epsilon. So I will not be able to detect the position of this particle with more accuracy than epsilon. Then the valid question to ask is that if I can talk about the classical trajectory of this particle within this resolution. So say I determine its position with some resolution at some initial time t equal to 0 and let it go. So for how long can we talk about the classical trajectory of this particle? So this relation, the uncertainty relation between x and x dot tells us that initially we would have some, given that our resolution is in epsilon, initially there will be some delta x dot that has to be at least of order of 1 over m times epsilon. Right? This is just a Heisenberg uncertainty principle, but written for x dot. So given that there is some uncertainty in the velocity of the particle, that can, with time, it can produce uncertainty in the position. What would be that? Let's call it delta. Let's call this delta x dot quantum. So then there will be some delta x quantum at some later time t. That would be of order of delta x dot quantum times t. It would be of order of t over m epsilon. So from here, we can determine the maximum time until which we can talk about this classical trajectory. Of course, when delta x quantum becomes larger than epsilon, then it is now the quantum uncertainty is bigger than our resolution. So therefore, the maximum time is determined by equating this. So delta xq t max is equal to epsilon. By equating this to epsilon, we can find the t max, and this gives us t max, which goes as is of order of m times epsilon square. Now, just to make sure that the dimensions are correct, remember that epsilon has dimension of x. So mx squared divided by t is like x times p, which is 1 in the natural units. I've said h bar to 1. So now what we see here is that, of course, this t max goes to infinity if I keep epsilon fixed and send m to infinity. In other words, if I make the commutator of x and x dot smaller, then I can talk and keep my resolution fixed. I can talk about the classical trajectory for this particle for longer and longer time. Now, a similar thing happens here. The commutator of phi and phi dot normalized with the resolution, or the typical value of fluctuations is going to 0 exponentially. Therefore, it makes sense to talk about a classical trajectory for this field for a very long time, exponentially long time. Okay, notice that here I never talked about anything like decoherence. This is just a free particle. Of course, decoherence happens when you have interactions, but really we don't even need to discuss that to treat the perturbations as a classical one in the superhorizon region. Any questions? What time is it? Okay. Yes. Uh-huh. Uh-huh. Well, there is no selection. All of those are part of the wave function. You should just think about the whole wave function of the system as being decomposed as a superposition of different classical trajectories. It's fine. It's very hard to understand it using your classical intuition. Uh-huh. I missed the second part. Uh-huh. Mm-hmm. No, no, you can just think of the evolution of this wave function as describing several possible classical, as the superposition of several possible classical trajectories. But the important point is that these different superpositions, they never interfere with each other. So you can restrict your attention to one or the other. Now, this is the point when you can switch to some statistical point of view. You say that the universe that now I'm measuring, I'm becoming entangled with this wave function. And then my measuring device is entangled with these different branches. And so there's this universe in which measuring device shows this value of x. Other universe measuring device shows the other values of x. They all evolve classically. It's the same thing. Now we get entangled with the CMB photons that know about the amplitude of this perturbation. Now when we look, we are the measuring device. Okay, so other questions? All right, so now we want to now translate what we learned about the correlation functions of this phi field, which was the perturbations of the inflaton field. We want to translate that into cosmological perturbations that are more relevant for the late time observations, namely adiabatic perturbations. So now I'm going to discuss something which perhaps it should have been part of the discussion of the background, but I didn't mention the number of efforts. So of course we talked about the fact that we need inflation to last long enough to solve the problem. So there is the notion of the number of efforts of inflation we defined. So it was NE equals log of the scale factor, say between the reheating time and some initial time. But one step that we didn't do, and it is very important, when we discuss the slow roll solution, so number of efforts is the log of the ratio of the scale factor, which you can write it as the integral of h times dt. So it's a very physical quantity. It is, you can imagine that there is a local observer who lives in this inflationary universe, a co-moving observer, and those co-moving observers like us, they measure the Hubble expansion rate. And then they integrate it in time. Of course, they have to be long-lived enough. We are relatively short-lived compared to the expansion rate of the universe. But if they, at that time, the time scales are shorter, so if this hypothetical observer measures the expansion rate and then integrates it in time, it is this NE, number of epochs. Now, during another thing that we saw was that the slow roll solution that we have is an attractor solution. What did it mean? It meant that the value of phi determined everything. So phi, or inflaton field, essentially was acting like a clock. It was telling us how far we are from the end of inflation. So this integral over time can be rewritten in this attractor phase. It can be rewritten as an integral over the scalar field over phi from some initial value of phi to the phi reheating. Notice that h and phi dot are determined by phi in this when we are on this attractor solution. Okay, so this is given a background, the slow roll solution. This is something computable. We can do it. We probably do it at some point. And it gives us, for instance, tells us how far we should go back, or what should be phi I, given the fact that reheating is happening at this point in the potential. How far should we go back in the field space so that we get the right number of epochs, which is 6. Now, we want to imagine the fact that, take into account the fact that, of course, phi is not homogeneous, but there are perturbations of phi. And in particular, we want to go to this regime, superhorizon regime. So consider some long wavelength perturbations of some perturbation of phi that crosses the horizon. After that point, when we are in the superhorizon regime, the gradient terms are negligible. So if we go back to this equation, the one that I wrote at the beginning, so this term is negligible in the superhorizon regime. Now, so far I neglected this. This was small, much less than h, and then before horizon crossing, even much less. H itself is smaller than this. Now, after horizon crossing, this equation is, you can think of it as just a perturbation of the background solution. So phi k, the fact that it has some finite wavelength, is the moment you neglect this term, is completely irrelevant. It's as if you are just solving the background equation of motion just with the perturbed value of phi. So what does it mean? It means that we can, instead of computing NE for the background field, we can imagine computing NE including one of these perturbations. Now, one important thing that goes into this discussion that I'm having now is that I am working at the level of linear perturbations. At the level of linear perturbations, different momenta, different wavelengths, they are decoupled from each other. They don't talk to each other. Therefore, I can just isolate one of them and talk about that. Then later, we can discuss, we will discuss non-Gaussianities that would, for instance, tell us that how the existence of one long wavelength perturbation might affect the other perturbations. But for now, we are doing linear perturbations, and we want to ask the following question. If we define some particular time slice that we call a reheating surface, at which phi is equal to constant. So phi of t and x is equal to phi reheating. We want to consider some long wavelength perturbation at some earlier time, in which we have one of these fluctuations. So there is some phi lambda. But this lambda, the wavelength of this is bigger than inverse Hubble, or in other words, this is super horizon. So in this regime, we can compute fluctuations of this number of EFOs. Why? Because what happens is that essentially what this fluctuation phi lambda does is that it introduces delta n, fluctuations in this number of EFOs in this region. So if you are an observer here, then you will experience a fluctuation in delta n, because from the time when this mode crossed the horizon until reaching to that reheating time, this integral has changed a little bit. Why? Because it takes a little bit of time for this to compensate this fluctuation phi. So there will be a delta n, which is given by minus h times this phi divided by phi dot. When at that particular time, so if it's phi lambda, then it is evaluated at that particular time when this mode is crossing the horizon. Apart from this time shift that is caused by these fluctuations of this mode, since we have this attractor solution, we are following exactly the same history as the unperturbed the slow-roll solution. So therefore, what happens is that if we choose at this late time, if we choose try to express the metric, but include these perturbations, then the metric with this particular choice of the time slice will have the following form. So there will be minus dt squared plus a squared, but there will be fluctuations of the scale factor, because remember that this NE is nothing but the log of the scale factor. So if there is a fluctuation in delta n, there will be a fluctuation of the scale factor that we call zeta, sometimes it's called R, is exactly this delta n. And this is a constant quantity. Why is it constant? Exactly because once you compensate with this extra expansion that you need because of this time delay, that is called by phi over phi dot. Apart from that, you follow exactly the same history as before. Okay, so now this is indeed something that just measures the adiabatic fluctuation. Remember that Julian talked about adiabatic perturbations, and he said that it is maybe the universal definition of adiabatic perturbations is that you just have the same history, thermal history or cosmological history, except that different points have some time shift with respect to each other. That time shift can be absorbed in this, expressed in this. Of course, in cosmology, you can have different ways of choosing your time slices. So there are different ways of quantifying that time shift. This is a very convenient one. And this is the thing that will be directly related to what we discuss in the late cosmology. So I see that time is this is probably also knows that time is Oh yes, the batteries. Okay, so using this formula, we can immediately compute the power spectrum, the two-point function for the adiabatic fluctuation zeta. And this is given by h star squared. I'm going to say what h star is in a second. Times momentum conserving delta function. So what is, and I should also say that to obtain this, I just use this relation. I use this relation and then the two-point function that we found for phi, and I use the fact that twice epsilon times m Planck squared h squared is equal to phi dot squared. So I use this relation to obtain this. Oh yes. Thank you. Yes, very importantly, there is a 1 over k cube here. And the star means that this is evaluated at the time of the horizon crossing of that particular k-mo. So in fact, if it wasn't because of this star, this would be an exactly scale invariant spectrum. But since h and epsilon slowly change with time, then that would translate into the slow k dependence that would cause a deviation from exact the scale invariance. Now, in the next lecture, I will talk about. I also mention the fact that there are tensor perturbations, and then we evaluate the tensor to a scale ratio, the tilt, and then we discuss non-Gaussianities. Okay, thank you. Questions? Yeah. Yeah, this is the idea behind delta informals. Oh, maybe I should say that if you are not very comfortable with this argument, you don't have to do it. It's just faster to get the result. But if you want to, you can just do some gauge fixing and compute things. Like what Julian said, there is a background that is isotropic, so you can decompose the perturbations into scales, vectors, and tensors. There is only one dynamical scalar and then tensor perturbations. So these are the two dynamical degrees of freedom, and one can, it's a linear perturbation theory, so one can do it, the study to death with no problem. Yes. Other questions? Yes. Yeah. There are two solutions, right? Because it's a second order ODE, right? F that I wrote is the one which, if you go to the limit of large k tau, it is oscillating. It has a phase that oscillates, I think, clockwise in time. And then there will be the other solution is just the complex conjugate of this. which has a solution that has a phase that changes, moves counterclockwise. So they are just the two opposite phases. What is BK? The second solution is there, right? It's just a dagger. No? You expand in terms of both of them. So these are the two solutions, F and F. And there is a natural code. F and F star are the two solutions. So you expand in terms of these two solutions. Now, why did I decide to multiply F by A and F star by A dagger? It's the same as when you look at harmonic oscillator. I mean, up to this one is actually completely arbitrary what you call A dagger. What is not arbitrary is this condition. The one that is multiplying what is called positive frequency mode, that should annihilate the vacuum. Yeah? I didn't understand the difference between the first and second. Yeah? Yeah? Yes, yes. Yes, indeed, because as you see in this diagram, right? So, of course, late and early, we are only talking, in this part of the discussion, we are talking about the inflationary phase. So, early means here, late means there. Here is subhorizon, here is superhorizon. Yes? Well, I choose a particular time slice that coincides with the fixed value of phi at the reheating time. And then I say that given the fluctuations of the inflaton field, the metric in that particular gauge coordinate choice, then the scale factor will not be uniform. The scale factor will change, fluctuate up and down. Why? Because as I was integrating h times dt to compute the scale factor from some initial time, I had to integrate a bit later or a bit more, a bit less or a bit more because of the jumps of the field. Yeah, that determines delta n, but remember that n is the log of the scale factor. So a delta n means is exactly zeta, the way I did, because I said that a goes to a times e to the zeta, take log of that, is log of a plus zeta, and that I identify with delta n, with the perturbations of the n. Yes? What about it? Okay, so for the inflaton fit, I did this trick that at some point I neglected the mass, right? So for the analysis of perturbations, I neglected this step. This would be an effective mass for the perturbations. Now, notice that this would be small corrections compared to that term. And also notice that what I did was I made the transition from phi to zeta after horizon crossing. Now, if I were to just stick to my variable phi, not to go to this delta and just solve for phi, what would happen is that phi would slowly evolve outside the horizon because this is not exactly 0. It would slowly change with time. You could decide to do this transition between the two variables phi and zeta at different times. What would happen is that phi would no, maybe let's start. Let's look here. Phi would slowly change in time, but so do h and phi dot. And then the result for zeta would remain constant. So here I did a simplification. This is like the fastest way to get to the result, to just make this conversion after horizon crossing. And this is star means that. You don't have to do it. If you do it at some other time, then you have to take into account the time dependence of phi and the time dependence of h and the time dependence of epsilon. And you'll get the same result. Yes? Or is it, maybe I should ask the moderator, can we continue or should we go discuss after? Okay. Uh-huh. I won't use it, but Julian already used it. Uh-huh. Right, exactly. There is no, in this scenario that I'm discussing, single feed inflation reheating has no effect on this perturbation because once it is a super horizon perturbations, you are just following the same background history except that you have this time shift with your neighbor. It's exactly the same history except that it's happening a bit later or earlier. Now, if you consider other scenarios like multi-feed inflation, then there can be different, the origin of the perturbations in a multi-feed inflationary model might be different. Let's say maybe some other field was around and that was fluctuating and that other field, say, determined how reheating is happening. The other field says here reheat at this time, there reheat at the other time. Then in those other cases, you can imagine a situation in which the super horizon perturbations will change in time. Either when you have multi-feed inflation or even in single feed if you deviate from attractor. Here I use the fact that we are on an attractor solution. Deviate from the attractor, again, the super horizon zeta solution can change. The state doesn't qualitatively change the story in the sense that what inflation does is to produce super horizon perturbations. Single feed inflation is very simple. It actually produces, to begin with, it produces super horizon adiabatic perturbation. If you have other more complicated model, you can, once you get super horizon perturbations, going to adiabatic perturbations is not impossible. Like if you go through a period of thermal equilibrium, quasi-equilibrium, whatever it is will be washed out except adiabatic perturbation. So still this important feature to put these seeds of perturbations at super horizon scales is an essential output of inflation that survives in those other manifestations. Yeah. Well, never under the assumption that I said. If you are talking about the single feed inflation, no, never. It could change. In multi-feed, you can have some changes there. Okay. Maybe we should have go for coffee after. Yeah. Uh-huh. Mhm. Okay, tomorrow I'm gonna talk about the potential, so maybe I can save this question for tomorrow. Okay, thank you.